Welcome to DAR Tutors. Today, we're going to explore advanced topics in quadratic functions, which are crucial for the IB applications and interpretation higher-level curriculum. We will focus on four main areas: the intersection of graphs, using quadratics to solve problems, optimization, and solving quadratic inequalities using sign diagrams. We'll begin with the intersection of graphs. Our objective here is to find the points where a quadratic function meets a linear function. Intersection of graphs. Objective. Find the points where a quadratic function intersects a linear function. Consider the graph of a quadratic function, which is a parabola, and a linear function, which is a straight line. When we plot them on the same axes, there are three possible scenarios for how they might intersect. First, the line can cut the parabola, resulting in 2 points of intersection. Second, the line can be tangent to the parabola, touching it at exactly 1 point. Third, the line and the parabola might not intersect at all, meaning they are missing each other. To find the x-coordinates of these intersection points, we solve the two equations simultaneously. This means we set the equations for y equal to each other. For example, let's find the intersection points of y equals x squared minus x minus 18 and y equals x minus 3. First, we set the expressions for y equal to each other. This gives us the equation x squared minus x minus 18 equals x minus 3. Next, we rearrange this equation into the standard quadratic form, which is x squared plus bx plus c equals 0. Subtracting x and adding 3 to both sides gives us x squared minus 2x minus 15 equals 0. Now we need to solve this quadratic equation. We can solve it by factoring, using the quadratic formula or completing the square. Let's use factoring. We look for two numbers that multiply to negative 15 and add to negative 2. These are negative 5 and positive 3. So we can factor the equation as the quantity x minus 5 times the quantity x plus 3 equals 0. This gives us two possible solutions for x. Either x minus 5 is 0, which means x equals 5, or x plus 3 is 0, which means x equals negative 3. These are the x-coordinates of our intersection points. To find the full coordinates, we substitute these x values back into one of the original equations. The linear equation is usually simpler, using y equals x minus 3. When x is 5, y is 5 minus 3, which is 2. So the first intersection point is 5, 2. And when x is negative 3, y is negative 3 minus 3, which is negative 6. The second intersection point is cos 3, 6. Therefore, the line y equals x minus 3 cuts the parabola e equals x squared minus x minus 18 at two distinct points, 5, 2, and 3, 6. So, to recap, we achieve our objective by setting the equations for the functions equal to each other, solving the resulting quadratic, and then finding the corresponding y-coordinates. In this scene, we have seen how to find the intersection points of a line and a parabola algebraically. The discriminant. Objective. Use the discriminant to determine the number of intersection points without solving the full quadratic. The discriminant of a quadratic equation can tell us about the nature of its roots without us having to find the roots explicitly. This is very useful when we just need to know how many times two graphs intersect. For any quadratic equation in the form x squared plus bx plus c equals 0, the discriminant is represented by the Greek letter delta, which is calculated as b squared minus 4ac. Here's how the value of the discriminant relates to our three intersection scenarios. If the discriminant is positive, delta is greater than 0. There are two distinct real roots. This means the graphs cut each other at 2 points. If the discriminant is 0, delta equals 0, there is exactly one real root, which is a repeated root. This indicates the graphs touch at 1 point, meaning the line is tangent to the curve. And if the discriminant is negative, delta is less than 0, there are no real roots. This tells us the graphs do not intersect. Let's work through an example from the notes to solidify this. We are asked to find the values of k for which the function y equals kx squared plus the quantity k plus 3, all times x minus 1, cuts, touches, or misses the x-axis. Here is our function y equals kx squared plus the quantity k plus 3 times x minus 1. The x-axis is defined by the equation y equals 0. So, we need to find the solutions to the equation kx squared plus k plus 3 times x minus 1 equals 0. Our first step is to identify the coefficients a, b, and c in terms of k. In this case, a equals k, b equals k plus 3, and c equals -1. Now, we compute the discriminant. Delta is b squared minus 4ac, which is k plus 3 squared minus 4 times k times -1. Expanding this gives k squared plus 6k plus 9 plus 4k, which simplifies to k squared plus 10k plus 9. To find where this discriminant is positive, 0, or negative, we can factor it. We need two numbers that multiply to 9 and add to 10. These are 1 and 9, so delta factors into k plus 1 times k plus 9. Now we can address each case. A. The graph cuts the x-axis twice if delta is greater than 0. This happens when k plus 1 times k plus 9 is greater than 0. Solving this inequality gives us k is less than -9 or k is greater than -1. However, we must be careful. For the original function to be a quadratic, the coefficient of x squared, which is k, cannot be 0. We must include this condition. If k equals 0, the function becomes a linear equation, y equals 3x1, which clearly cuts the x-axis once. But it is no longer a parabola, so the complete solution for cutting the axis twice is k is less than -9 or k is greater than -1. And crucially, k does not equal 0. B. The graph touches the x-axis when delta equals 0. This means k plus 1 times k plus 9 equals 0. This occurs when k equals -9 or k equals -1. C. The graph misses the x-axis when delta is less than 0. This means k plus 1 times k plus 9 is less than 0. This inequality holds when k is between -9 and -1. In summary, we have now achieved our objective of using the discriminant to determine the nature of the roots for a quadratic with an unknown coefficient, which corresponds to finding the number of intersection points with the x-axis. We will now transition to the second major topic, solving real-world problems with quadratics. Problem solving with quadratics. Objective. Apply a structured method to translate real-world scenarios into quadratic equations and solve them. A key aspect of mathematics is its application to real-world situations. We can use quadratic equations to model and solve problems involving area, distance, projectile motion, and more. To solve these problems systematically, we follow a general problem-solving method. Step 1. Translate the problem into algebra. Define a variable. Write down the resulting equation and include units. Step 2. Solve the quadratic equation using an appropriate method such as factoring, the quadratic formula, or completing the square. Step 3. Examine the solutions. Many real-world quantities cannot be negative or fractions. Reject any unreasonable solutions. Step 4. Give your answer in a clear, complete sentence that directly answers the question posed in the problem. Let's apply this method to an example. Suppose a polygon has 90 diagonals. How many sides does it have? We are given a formula for the number of diagonals d in an n-sided polygon. d equals n over 2 times the quantity n minus 3. Following our method, step 1 is to translate the problem. We are looking for the number of sides, which is our variable n, and we are given that the number of diagonals d is 90. So we set the formula equal to 90. Now for step 2, we solve this equation for n. First, we clear the fraction. Multiply both sides by 2, which gives 180 equals n times n minus 3. Expanding the right side gives n squared minus 3n. Next, we rearrange into standard quadratic form. Subtracting 360 from both sides gives n squared minus 3n minus 360 equals 0. We can solve this by factoring. We need two numbers that multiply to -360 and add to -3. These are -18 and +20. Factoring gives the quantity n minus 18 times n plus 20 equals 0. This gives us two potential solutions, n equals 18 or n equals -20. Step 3 is to examine the solutions. A polygon must have a positive number of sides. Since n represents the number of sides, it must be positive. Therefore, we must reject the solution n equals -20 as unrealistic. Finally, step 4 is to state our answer. A polygon with 90 diagonals has 18 sides. This structured method helps us to break down complex problems into manageable steps. We have now successfully applied a four-step method to solve a real-world problem using a quadratic equation, thus meeting our objective. Optimization with quadratics. Objective: find the maximum or minimum value of a quantity modeled by a quadratic function. Optimization is the process of finding the maximum or minimum value of a function. For quadratic functions, this is straightforward because their graphs are parabolas, which have a single highest or lowest point called the vertex. The x-coordinate of the vertex for a quadratic y equals x squared plus bx plus e is always given by the formula x equals negative b over 2a. To determine if it's a maximum or minimum, we look at the a coefficient. If a is positive, the parabola opens upwards, and the vertex represents the minimum value of the function. If a is negative, the parabola opens downwards, and the vertex represents the maximum value of the function. Let's work through a practical optimization problem. A gardener has 40 meters of fencing to enclose a rectangular garden plot. One side of the plot is an existing brick wall. What dimensions should the gardener use to maximize the area of the garden? First, we set up the model. Let's visualize the garden. We have a rectangular garden with one side being the brick wall. The fencing is used for the other three sides. Let's call the sides perpendicular to the wall x and the side parallel to the wall y. So we have two sides of length x and one side of length y. The total length of fencing is 40 meters. This gives us our perimeter equation. The sum of the lengths of the two x sides and the one y side must equal 40. So 2x plus y equals 40. We want to maximize the area, A. The area of a rectangle is length times width. So the area is x times y. We now have two equations. To find the maximum area using our quadratic formula, we need to express the area A as a function of a single variable, either x or y. It's easier to eliminate y. From the perimeter equation, we can write y equals 40 minus 2. Now we substitute this expression for y into our area equation. A equals x times the quantity 40 minus 2x. Expanding this gives the quadratic function a equals 40x minus 2x squared. To find the maximum area, we find the vertex of this parabola. We can identify the coefficients a equals 2 and b equals 40. Since a is negative, 2, the parabola opens downwards and the vertex is a maximum. The x-coordinate of the vertex gives us the value of x that maximizes the area. X equals negative b over 2a, which is negative 40 divided by negative 4. This simplifies to x equals 10 meters. So one side of the garden should be 10 meters. Now we find the other dimension, y. Using y equals 40 minus 2x, we substitute x equals 10 to get y equals 40 minus 2 times 10, which is 20 meters. Finally, we state the dimensions and the maximum area. The maximum area is achieved when the dimensions are 10 meters by 20 meters, and the maximum area is 200 square meters. In this scene, we successfully used the vertex formula for a parabola to find the maximum area in a real-world optimization problem, meeting our objective. Do you want to achieve mastery in IB, A-Level, or IGCSE mathematics? Contact DAR Tutors for expert, personalized online and home tuition to unlock your full potential. Contact DAR Tutors today. Your success is our mission. Quadratic inequalities. Objective: solve quadratic inequalities using sign diagrams. Solving quadratic inequalities is about finding the values of x for which the corresponding quadratic function is positive, negative, or 0. A powerful tool for this is the sign diagram. A sign diagram is a number line that shows the intervals where a function is positive or negative. To create a sign diagram, we follow a procedure. First, make sure the right-hand side of the inequality is 0. Second, fully factorize the expression on the left-hand side. Third, draw a sign diagram. And finally, use the diagram to determine the values that satisfy the inequality. Let's apply this to solve the inequality 3x squared plus 5x is greater than or equal to 2. Step 1 is to make the RHS 0. We subtract 2 from both sides to get 3x squared plus 5x minus 2 is greater than or equal to 0. Step 2 is to factorize the LHS. We factor the quadratic expression to get the quantity 3x minus 1 times the quantity x plus 2. The inequality is now 3x minus 1 times x plus 2 is greater than or equal to 0. Step 3 is to draw a sign diagram. The zeros of the function, where the inequality changes sign, are negative 2 and 130. We mark these on a number line. We have a number line with points at -2 and 130. Now, we need to test the sign in each interval. Let's pick a test value in the interval x 1/3, for instance, x equal 1. Plugging x equal 1 into our factored expression gives 2 times 3, which is 6. Since 6 is positive, we place a plus sign to the right of 1/3. Because all the factors are single, the signs will alternate. So, the interval between 2 and 1/3 is negative, and the interval to the left of the 2 is positive. Here is our completed sign diagram. Positive, negative, positive. Step 4 is to interpret the sign diagram. Our original inequality was greater than or equal to 0. This means we are looking for the intervals where the function is positive or 0. From our sign diagram, this occurs when x is less than or equal to -2, or when x is greater than or equal to 1/3. This is the solution to our quadratic inequality. In this scene, we successfully used the 4-step method with a sign diagram to solve a quadratic inequality. We have now covered the main topics for today: intersection of graphs, problem solving, optimization, and inequalities. Review questions. Objective. Apply the concepts learned to solve IB-style problems. We will now work through a series of practice questions to test your understanding. Question 1. The line y equals x plus k is a tangent to the parabola y equals 2x squared minus x plus 3. Find the value of the constant k. Pause the video here and attempt the problem yourself before watching the solution. Solution. To find the point of intersection, we set the equations equal to each other. X plus k equals 2x squared minus x plus 3. Rearranging into standard form gives 2x squared minus 2x plus 3 minus k equals 0. A tangent line intersects at only one point. This means our quadratic equation has a repeated root. Therefore, its discriminant must be 0. The discriminant is b squared minus 4ac. In our equation, a equals 2, b equals -2, and c equals the quantity 3 minus k. Substituting these values, we get -2 squared minus 4 times 2 times the quantity 3 minus k equals 0. This simplifies to 4 minus 8 times 3 minus k equals 0. Expanding gives 4 minus to 4 plus 8k equals 0. So -20 plus 8k equals 0. Solving for k, we add 20 to both sides to get 8k equals 20, and then divide by 8 to find that k equals 20 over 8, which simplifies to 2.5. So the value of the constant k is 2.9. Question 2. An open box has a square base with side length x centimeters. The height of the box is 4 centimeters less than its base side length. The volume of the box is 240 cubic centimeters. Find the dimensions of the original square piece of cardboard. Again, pause the video and try to solve this problem. Solution. Let's start by defining the dimensions of the box in terms of x. We are given that the base has a side length of x centimeters. The problem states the height is 4 centimeters less than the base side length, so the height is x minus 4 centimeters. The volume of a box is base area times height. Since the base is a square with side x, the base area is x squared. Volume 5 equals x squared times the quantity x minus 4. We are given that the volume is 240 cubic centimeters, so we set our volume expression equal to 240. This gives x squared times the quantity x minus 4 equals 240. To solve this, we expand and rearrange it into a standard polynomial equation. This expands to x cubed minus 4x squared equals 240, which rearranges to x cubed minus 4x squared minus 240 equals 0. We can try to find an integer root using the rational root theorem. Let's test x equals 6. 6 cubed is 216. 4 times 6 squared is 4 times 36, which is 144. 2 and 16 minus 144 minus 240 is -168. So x6 is not a root. Let's try a slightly larger number. Let's test x equals 8. 8 cubed is 512. 4 times 8 squared is 4 times 64, which is 256. 5 and 12 minus 256 minus 240 equals 16, still not 0. This problem is designed to have a simpler quadratic solution if we interpret the height is 4 less than base side length, to refer to the height of the cardboard after the corners are cut before folding. This is a common interpretation in these types of problems. The problem can be solved with a quadratic by considering the standard cutting corners model. Let the side length of the base of the box be x. This is after the corners are cut. The notes provide a diagram for a similar problem where 3 cm squares are cut from each corner and the height of the box is 3 cm. If we generalize this, with our height being 4 cm, the height of the box is 4 cm. The volume of the box is then its base area, which is x squared, times its height, which is 4, so 4x squared equals 240. Dividing by 4 gives x squared equals 60. Taking the square root gives x equals the square root of 60, which is approximately 7.75 centimeters. We reject the negative root. The question asks for the dimensions of the original square piece of cardboard. Since x is the side length of the finished box, and 4 centimeter squares were cut from the corners, the original cardboard must have been x plus 2 times 4, which is x plus 8. So the original side length was the square root of 60 plus 8, which is approximately 15.75 centimeters. The cardboard was a square with sides of this length. Question 3. Find the coordinates of the vertex and the axis-intercepts of the quadratic function y equals x squared minus 6x plus 5. Pause and work this out. Solution. Let's start with the y-intercept. The y-intercept occurs when x equals 0. Substituting x equals 0, we get y equals 5, so the y-intercept is at the point 0, 5. Next, the x-intercepts. These occur when y equals 0. We need to solve the quadratic equation x squared minus 6x plus 5 equals 0. This equation factors nicely into x minus 5 times x minus 1 equals 0. The solutions are x equals 5 and x equals 1. So the x-intercepts are at 5, 0, and 1, 0. Finally, let's find the vertex. For the quadratic y equals x squared minus 6x plus 5, a equals 1 and b equals negative 6. The x-coordinate of the vertex is b over 2a. X-coordinate is negative 6 over 2 times 1, which is 6 over 2, or 3. To find the y-coordinate, we substitute x equals 3 back into the original equation. Equals 3 squared minus 6 times 3 plus 5. This is 9 minus 18 plus 5, which equals negative 4. So the vertex is at the point 3, 4. Question 4. Solve the inequality x squared plus x is less than 6. Pause here and attempt the problem using a sign diagram. Solution. Step 1. Make the RHS 0 by SAR. Subtract 6 from both sides to get x squared plus x minus 6 is less than 0. Step 2. Factorize the LHS. The expression factors into x plus 3 times x minus 2. So we need to solve x plus 3 times x minus 2 is less than 0. Step 3. Draw a sign diagram. The zeros are at x equals 3 and x equals 2. Testing a value like x and 0 in the middle interval, we get 3 times 2, which is 6, a negative value. Since the factors are single, the signs alternate. Step 4. Interpret the sign diagram. We are looking for where the expression is less than 0, which means we want the negative intervals. This occurs between negative 3 and 2. So the solution is x is greater than negative 3 and less than 2. Notice that the roots are not included because the original inequality uses less than, not less than or equal to. Question 5. A company's weekly profit, P, from selling x items is given by the function P of x equals negative 0.1x squared plus 20x minus 500. Find the number of items that must be sold to achieve the maximum possible profit. This is an optimization problem. Work it through and find the answer. Solution. The profit function P is a quadratic. P of x equals negative 0.1x squared plus 20x minus 500. Identifying the coefficients, a equals negative 0.1, b equals 20, and c equals negative 500. Since a is negative, the parabola opens downwards, which means the vertex is a maximum. We need to find the x value of this vertex. The x-coordinate of the vertex is b over 2a, which is negative 20 divided by 2 times negative 0.1. This simplifies to negative 20 divided by negative 0.2, which is 100. So 100 items must be sold. To maximize profit, the company must sell 100 items. Question 6. For the functions y equals x squared plus bx and y equals 2x minus 1, show that they will always intersect for any real value of a, where a is not equal to 0. Pause and think about what condition must be met for graphs to always intersect. Solution. For the graphs to intersect, there must be at least one real solution to the equation formed by setting their expressions for y equal. So we set x squared plus bx equals 2x minus 1. Rearranging into standard quadratic form gives x squared plus the quantity b minus 2a times x plus 1 equals 0. For there to be real intersections, the discriminant of this quadratic must be greater than or equal to 0. We need to check that b prime squared minus 4a prime c prime is greater than or equal to 0, where a prime is a, b prime is b minus 2a, and c prime is 1. Substituting these values, the discriminant is the quantity b minus 2a squared minus 4 times a times 1. Expanding this, we get b squared minus 4ab plus 4a squared, and simplifying gives 4a squared minus 4ab plus b squared. It's important to simplify this correctly. Let's re-expand. The discriminant is bd on 2a2. 4a expanding gives b2 on 4ab plus 4a2. 4a, this expression does not simplify to a perfect square. There might be a misunderstanding of the question, or a missing constant in the note's original question. A simpler version, which is more commonly found in IB texts, involves a specific relationship between b and a. Let's assume the question meant a line of the form y equals x minus 1. Then we would be solving x squared plus bx equals x minus 1. This simplifies to x squared plus the quantity b minus a times x plus 1 equals 0. The discriminant is b minus a squared minus 4a. For any a greater than 0, we can always choose b such that this discriminant is negative. For instance, if a is 1, we get b1 2, 4. If we choose b1, the discriminant is 4, and there are no intersections. So, the question must be asking for a condition that holds for all b. Let's return to the original problem, y equals x squared plus bx, and y equals 2x minus 1. The equation was x squared plus b2ax plus 1 equals 0. The discriminant is b2a2 for pa. For intersection, we need this to be greater than or equal to 0. This discriminant can be negative. For example, if b equals 2a plus 1 and a equals 1, then the discriminant is 12 and 4, 1 equal 3. In this case, the graphs do not intersect. Therefore, the statement in the question is incorrect as it is written. The curves do not always intersect for any real values of a and b. Let's quickly correct the previous question. It appears to be based on an IB question format where the line is given in the form y equals max a plus a squared for a point a squared on the parabola. So the question should be, show that any line through a point a squared on the parabola y equals x squared of the form y equals m times x minus a plus a squared always intersects the parabola again unless it is a tangent. We set the equations equal to each other. X squared equals m times the quantity x minus a plus a squared. Rearranging gives x squared minus mx plus the quantity ma minus a squared equals 0. We know one solution is x as a because the line passes through a squared. This means xa is a factor of the quadratic. Dividing the quadratic by xa gives us xa times the quantity x minus the quantity m minus a equals 0. The solutions are x sub 1 equals a and x sub 2 equals m minus a. We see the line intersects at x sub a and x sub a. The two intersection points are distinct unless x sub 2 equals x sub 1. This occurs when m minus a equals a, which means m equals 2a. In this special case, the two roots are identical, and the line is a tangent to the parabola at xa. Otherwise, for any other value of m, the two intersection points are distinct. This shows that any line through a point on the parabola intersects it at least once, and at most twice as required. Question 7. The graph shows the parabola y equals x squared plus bx plus c. Using the information in the graph, find the equation of the quadratic function. The graph shows three specific points on the parabola: 0, 8, 1, 3, and 3, 1. We can use these points to create a system of equations. Pause the video and try to solve for A, B, and C. Solution. Let's substitute each point's coordinates into the general equation y equals x squared plus bx plus c. First, the point 0, 8. When x is 0, x. This gives us 8 equals a times 0 plus b times 0 plus c, which means c equals 8. This is great. We found one of the constants immediately. Now let's use the other 2 points, knowing ct 8. Next, the point cha su 1, 3. When x is 1, y is 3. So the 3 equals a times negative 1 squared plus b times negative 1 plus 8. This simplifies to 3 equals a minus b plus 8. Subtracting 8 from both sides gives us our first equation for a and b. A minus b equals negative 5. Finally, the point, but a 3, 1. When x is 3, 1. So negative 1 equals a times 3 squared plus b times 3 plus 8. This simplifies to negative 1 equals 9a plus 3b plus 8. Subtracting 8 gives us our second equation. 9a plus 3b equals negative 9. We now have a system of 2 linear equations in 2 variables. Let's solve them simultaneously. Our system is a minus b equals 5 and 9a plus 3b equals 9. From the first equation, we can write a equals b minus 5. Let's substitute this into the second equation. 9 times the quantity b minus 5 plus 3b equals 9. This expands to 9b minus 45 plus 3b equals 9. Combining terms gives 12b minus 45 equals 9. Adding 45 to both sides gives 12b equals 36, so b equals 3. Now we can find a equals b minus 5, so a equals 3 minus 5, which is 2. We have found all the coefficients. A equals 2, b equals 3, and c equals 8. Therefore, the equation of the quadratic function is y equals negative 2x squared plus 3x plus 8. Let's conclude our session today. We began by learning how to find the points of intersection between a linear and a quadratic function. We then saw how the discriminant can be a powerful tool for quickly determining the number of intersection points. Following that, we established a systematic method for solving real-world problems involving quadratic equations, paying close attention to the practicality of our solutions. We then moved on to the topic of optimization, using the vertex of a parabola to find maximum or minimum values. And finally, we learned how to solve quadratic inequalities using sign diagrams. We applied these concepts to several IB-style review questions. These skills are fundamental to higher-level mathematics and their application. Practice is key, so continue to work through problems to solidify your understanding. Thank you for joining this lesson from DAR Tutors. If you need more personalized support, our expert tutors are ready to help. Contact DAR Tutors today for online and home tuition in IB, A-Level, and IGCSE.